Bismillahirrahmanirrahim. In the previous video, we studied the double sideband compressed carrier amplitude modulation. In this video, we are going to study the demodulation. So to recover the message signal from the modulating signal by retranslating the shifted spectrum back to its original position is called demodulation. If you remember, in modulation, we shifted the spectrum of the message signal to a higher frequency. Now in demodulation, we are going to reshift the shifted spectrum back to its original position. Now what is the process of the demodulation? We need to multiply the incoming modulated signal, which was the m of t cosine omega ct, by a carrier cosine omega ct followed by a low pass filter. So this will result in the recovery of the original signal. If you remember, in case of the modulation, we have a message signal m of t, and that message signal was multiplied by the carrier signal cosine omega ct. As a result, we have the modulated signal m of t cosine omega ct, and as a result, the frequency of the message signal was shifted by plus minus fc. Now in demodulation, we are going to multiply this modulated signal. This is my modulated signal. We are going to again multiply with the carrier, which is cosine omega ct. After multiplying with the carrier, and then we are going to pass it to the low pass filter. So after multiplying with the carrier and then passing it to the low pass filter, the shifted spectrum, which was at plus minus fc, will be returned to its original position. As a result, we are going to recover the original signal. So this is our block diagram. This is our modulated signal, which is m of t cosine omega ct, and this is called the modulated signal. Now we are going to multiply this modulated signal with a carrier, which is cosine omega ct. After multiplying with the carrier, for example, we have a function e of t. Then this function e of t is going to be passed with the low pass filter. When it is passed to the low pass filter, the higher frequency components will be filtered out. As a result, we are going to have the message signal half of m of t. Now in this case, the message signal has an amplitude half of the original message signal. So that's why we need to multiply with the 2 cosine omega ct. So if we multiply this with 2 cosine omega ct, we are going to get the original signal, which is m of t. So this is the block diagram of the demodulation. Now let us perform it mathematically. So we have a modulated signal, which is again m of t cosine omega ct. Now this m of t, the first step is to multiply with this with the carrier, which in this case I am going to take 2 cosine omega ct. So let me name it as the function e of t. So this will be equal to e of t is equal to 2 mt cosine square omega ct. So this will be equal to e of t is equal to 2 m of t. Now we are going to use the trigonometric formula, and this will be 1 plus cosine 2 omega ct divided by 2. So this 2 will be cancelled out with this 2. As a result, we are going to have e of t is equal to m of t. I am going to multiply this over here, and m of t cosine 2 omega ct. Let me name it as equation 1. Now we are going to convert this into a frequency domain by applying the Fourier transform. And by applying the Fourier transform here, we are going to use the frequency shifting property. So this will be e of t is equal to m of f, where f is the frequency domain, and here I am going to apply the frequency shifting property. So this will be half into f plus 2fc plus m into f minus 2fc. Now this e of t will be passed to the low pass filter. Now when I pass it to the low pass filter, this higher frequency components, which are plus minus 2fc, is going to be filtered out. And when these components are filtered out, so this thing is going to be filtered out. So in that case, here I am going to have e of f. So in that case, let me denote it by capital E of f. So in that case, e of f is going to be equal to m of f, because after passing it to the higher frequency, this components is going to be filtered out. So once these components are filtered out, we are going to have e of f is equal to m of f. Now I am going to take the inverse Fourier transform. So this will be E of t is equal to m of t, which is our original signal. So that in the demodulation process, we are going to recover the original signal from the modulated signal. And if you can see over here, I have mentioned the process that multiply the incoming modulated wave signal, which is m of t cosine omega ct, by a carrier cosine omega ct. So here I have multiplied by a carrier cosine omega ct, and to have the magnitude equal to the original signal, I am going to multiply with 2. So I have multiplied with 2. Take the Fourier transform, we are going to get this thing. After taking the Fourier transform, the next step is to pass it to the low pass filter. After passing it to the low pass filter, these frequency components are filtered out, and as a result I have the signal m of f. And when I take the inverse Fourier transform, when I come back to the Fourier transform, I have the original signal m of t. Now this method is called synchronous detection or coherent detection. Why is it called the synchronous detection or coherent detection? Because if you can have a look in the modulation, we used exactly the same carrier of same frequency and phase as the carrier used for modulation. So if you can have a look, we use the carrier cosine omega ct for modulation, and we have used the same carrier cosine omega ct for demodulation. That is why this is called the synchronous detection or coherent detection.